Good day once again, students. Today we are going to look at some questions in fluid mechanics. You see, this is one of the areas that scares students a lot. Not because it is very difficult, but it needs you to understand the basic principles very well. Just what we are going to look here in this first video on fluid mechanics, it's has to do with one or two principles, just the Archimedes principle and law of flotation. The Archimedes principle and law of flotation. That's what it has to do with. All the questions I'll be talking about, most of the calculation here has to do with that. And I'll also talk about the type of flow, turbulent flow, and streamline flow. Most of the questions here have to do with that. Now, I have the first question here. It says, these are past questions. Forget about the board you are doing. As far as physics is concerned, physics is physics. As far as you have upthrust, flotation, Archimedes principle, density, and all these things in your syllabus, you are good to go. It does not matter what board you are writing. Along a river, there are changes in speed of water due to natural obstacles, such as bends and rocks. And of course, we know that. At a bend, the water on the inside of the bend is usually shallower than the water on the outside of the bend. Of course, we don't need to give reason to this. Of course, the geography students, of course, surely have reasons for this. We know that we did that when we were in secondary school, and I'm sure you are still doing it today. While the water on this side of the bend is usually, of the inside of the bend, is usually shallower. Shallower means it is closer to the base of the river is closer to the top. That means you have a smaller body of water here than here. This side is deeper. This side is much deeper than the inside. That's what it's telling us of the bend. Now, what is the question here? What is the question here? Don't forget that it has told you that because of due to natural obstacles such as bed and rocks, so you have shallower. So if it is shallower, that means the base is closer upward. Now, suggest why the speed of water is lower. This is the question now. Based on what they have just told you, this is the question. Based on that, suggest why. When they ask you to suggest, they are asking you to use the principles you know, combined with common sense, or combined with your knowledge of physics, or with your knowledge of physics and science generally, to answer this. When they say suggest, you are suggesting now to them based on what you think. It may vary. You may have variable answers, but all of them will be in the marking scheme, and it will make sense. The answer must make sense. So suggest why the speed of the water is lower at the inside of the bend than at the outside of the bend. Somebody, you cannot just say, oh, because they put a pump there, so that one is faster. That does not make sense. You have to suggest something, because you say just bring it from the blue. You can't just bring it from anywhere out of the blues. Just bring it out. No, you have to make reasonable suggestion. Now, what do you suggest here? Remember, when I drew for you, this is like a pipe now, without a cover. It's like a pipe without a cover now. Remember when I drew for you the pipe, I had pipe drawn for you like this. And when I drew for you the layers of water, the closer the layer of water to the you can see the water this is flowing. It's like that. It's flowing this way. This is ahead. The one, look at it, we cut the pipe like this. But for this pipe, here is a river. It has no cover. So the water closer to the solid has more drag force. There's more friction between here and here. If this one is slow, because the frictional force between the solid here and the layer here is higher, this one is already moving slower. The drag force here will be more than this. It increases to the center. You know that from the diagram of the pipe I drew for you in my video of type of flow. You remember that from my video. So because it is shallower, so the closer the water that is closer to the base, because the water at this end is shallower, is closer, the body of water is closer to the base. And you say, what do you have at the base? You have rocks also, you have pebbles also, you have sand also. So it's not smooth. But the water on top here is floating on top of more water. So it is moving with less drag force. The water on top this way is moving with less drag force than the water here. Just like the water, the head of water here is moving with less drag force than the water here. So they say, so guess why the speed of the water is lower at the inside of the bend than at the outside of the bend? Because it is shallower, so it has more. I think it is only 1 mark. It's only 1 mark question. It's only 1 mark. It's just a mark. It's just a mark. So because that place is shallower, so the drag force, I won't call it frictional force now because it's in water, the drag force is higher. The drag force is higher because it is closer to the solid base. Question number 2. On a straight section, on a straight section of the river, the water becomes very turbulent around a large rock. That is the large rock there. Complete and label the diagram below to show. Complete and label the diagram below to show the flow of water around the rock. The flow of water around the rock. Now, look at it. If this rock, if this place was smooth like this, if it was smooth like that, of course, I will have no turbulence at all. I will have no turbulence at all. If this place was smooth throughout like that, I will have no turbulence. It will just flow, streamline flow like that. However, I am not going to have that because, one, this place is rough. So as it approaches that rough and solid, it does not only, they don't all change direction together because the place is not smooth like that, but you don't write that. So it starts messing around. It starts messing around. It starts messing around. Yes, it will still go, but it starts messing around. It starts messing around. It starts messing around. It's still going, but it starts messing around. It does not flow smoothly again. Same thing this. And don't forget there's a sharp angle here. Once you cross a sharp angle, I told you when I was teaching you the flow of liquid. Once you cross a sharp angle, once you pass a sharp angle, what you see after the sharp angle is turbulence, mixing of layer. So don't allow the layers to mix before the sharp angle. Try and look at the point where you have the sharp angle is right here at the middle. So after that sharp angle, try and this can go straight because it is getting further and further away. Now I will still make this one a little curve, and I can have my edges formed. I can have edges here if I like. So you can see now that because it is getting close to a rough edge, it becomes wavy. Then when it crosses the sharp angle, then missing of layer occurs. Missing of layer occurs. mixing of layers occurs because it passes the sharp angles, and as it's getting close to the rough edges of the rock, it's not smooth. Then what happens? Just like the rough below the river, it is not smooth. It's not as smooth as if you have just a very, very smooth surface, frictionless surface there. No, you have something that is rough also below the river we showed you earlier. Now, a small drop of dye, this is number 2 now, we finished number 1. A small drop of dye was injected into the center of a flow, the center of the flow of a liquid. This is the flow of the dye. Liquid was flowing like this, don't forget, liquid was flowing like this, and if the dye, I said the flow of a liquid moving freely through a pipe. This was repeated for a pipe with a smaller diameter. The dye was seen to take the following path. Now, it's a smaller diameter pipe. This is a bigger diameter pipe. Now, what happens here? Here, this is the ink. Liquid is flowing. Liquid is flowing this way. You have liquid everywhere. The ink. You have the ink flowing. You have the ink flowing. The ink is flowing. The ink is flowing. The ink is flowing. Why am I drawing it as laminar flow? Because the dye they injected in is also flowing in a laminar manner, in a straight manner, without bending. So that means this flow of liquid air is a laminar flow. But look at, when the dye was injected into this smaller pipe, you can see how you have different directions, sudden change in direction, and erratic, and it is chaotic, a chaotic flow. So it says, describe the differences between the flow of the liquid through the large diameter pipe and the smaller diameter pipe. Of course, you are saying that this flow here is what? Is laminar flow, and the flow here is turbulent flow. So what they are asking you in essence is to tell them the differences between laminar flow and turbulent flow. They don't have to state it exactly like this. A student who does not know that this is laminar or streamline and this is turbulent, the student will be in trouble. So now they are asking you the differences, and of course when you are telling the difference, since they did not tell you this is laminar or turbulent, the first difference you have to write. Since they did not tell you the names, the first difference will be the name. You will say this is laminar flow, this is laminar, and this is turbulent. Turbulent flow, laminar flow and turbulent flow. So you have that. Or streamline flow and turbulent flow. You have that. That's the first difference. Of course, it is 3 marks. Okay. Now tell them more. Tell them more. Laminar flow, turbulent flow. If you say this one has something, behaves one way, and this one behaves in a different way. For writing that this one has behaved one way, you get 1 mark, and this one behaves in a different way opposite this, you get another mark. So you say this one is, there is no sudden change of direction. There is no sudden change of direction here. Here you have sudden change of direction. There is change of direction. There is always change of direction there, but this one, there is no sudden change of direction at a point. But there, if you look at a point in the water and you are looking at it, you see change of direction. You mark, so you see change of direction here. Sudden change of direction occurs here. It does not occur at a point. It does not occur here. Good. Another one. Another difference between laminar and turbulent flow. Another difference between that you can easily see here. All the differences occur because there's no change of direction here. There's change of direction here. You are saying that the velocity over time is constant here. The velocity here changes. How do you know the velocity changes? Direction is changing. So velocity changes. So the change of direction. This is just enough for you. Wasting your time to write so many other differences, and if you have the time, write all the differences. But first, you must state that this is laminar, this is turbulent. You have all the characteristics in your note if you have watched the video on laminar and turbulent flow. You have watched my video on laminar and turbulent flow. Suggest a possible reason other than the diameter for the difference in the flow between the two pipes. Suggest different reasons other than the diameter. For this to be laminar, it means it's flowing steadily and it's flowing slowly. The velocity here is low, the velocity here is high. It should have been one of your differences. So why is the velocity here high? Why should the velocity here be higher than the velocity here? There's so many things can be responsible for it. You see? Maybe before this pipe, there was the pump. There was the pump. It makes sense. The pump makes sense in this case now. There was the pump. Maybe this was pumped. Then it's moving faster. Maybe the temperature here is higher. If the temperature here is higher, what happens? There will be increase in the speed. Why? Because viscosity will reduce. It's a liquid, not a gas. For gases, at higher temperature, what happens? You should be able to tell me. It's opposite for that of liquid. So it's a liquid. When the temperature is high, it becomes less viscous. When it becomes less viscous, it flows faster. A more viscous fluid flows slowly. So you see, maybe the temperature is higher here. That's the point. Maybe there was a pump which speed up the which causes it to move faster just before it entered the pump. Okay? These are reasons. So you have talked about the pump, you have talked about the velocity, and you've talked about the temperature. All makes it. If you talk about the temperature, it becomes less viscous. When it's less viscous, it moves faster. It becomes more turbulent. And the temperature also can increase kinetic energy. You know that. You can come from that angle. A ship is loaded. All these questions have been answered since they are easier than what I'm going to talk about now. A ship is loaded. As a ship is loaded, it moves. Don't forget, you must have watched my video on the on upthrust, flotation, and the importance, the advantages of upthrust and flotation. You see, I cannot actually remember the name of that, the topic, the name of the video over there, but when you're talking about the uses of the upthrust and flotation, the practical uses of it. Okay? Now, as a ship is loaded, it moves lower in the water so that the water level rises up the side of the ship. Plimsoll line is one of the things I discussed in that video. Plimsoll lines on the side of the ship. This shows the maximum depth to which the ship can be immersed. Let's assume I have a ship like this. I have a ship like this. On water. On water. This same ship I have on water here. This ship can sink in. It can go into the water. Sorry. I need to move this one to one side. Really sorry. Now, the ship can move in. Can move in. Depending on two things. As the ship floats, two forces are acting on it. As it floats, two forces are acting on it. Don't forget that. So marks have been here to show at different water what will happen. Let's look at the question. It is said that the plimsoll line on the side of the ship shows the maximum depth to which the ship can be immersed when loaded with cargo. So when you load it now, weight increases and it sinks in more. It sinks in more. It sinks in more. So when it sinks in, these lines are by the side here of the ship. Okay? I'll come back to that. The maximum loading depth depends on the ship's dimension, the time of the year, and water density. We'll come to that. Use the idea of upthrust to explain why a ship will be lowered in the water when loaded. Why will it sink a little? Why will it be lowered a little? Why will it be lowered? Why will it sink? Not totally sink. Why will it go down a little? At least to an extent, when depending on the amount of load you have in it. From common sense, you say, yes, it will go down because the weight is increasing. Okay, but that's not physics. Now, when the ship was here, two forces are acting on it. One is weight, and the upthrust of water. Is weight and the upthrust of water, which is exactly equal to the weight. That's why I'm making them the same line, equal line. And the upthrust of water. And what is the upthrust of water? That is the weight of the displaced water. Don't forget that. Upthrust is always the weight of the displaced water. Don't forget that. So these two are equal. But here when it was empty, a little water was displaced. Not too much water was. A little water, amount of water was displaced. A little amount of water was displaced. Let me remove this, it's causing some problem. Not too much water was displaced. So because the ship was also not too heavy, the weight was small, and the upthrust is also small. Wherever the ship may be, whatever level it may go in, if it likes, let it just touch as it is touching. If it likes, let it go deep inside. Deep inside. Let it go deep and deep and deep inside. Let the ship go inside, deep and deep. Inside, deep, 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 deep. Only the neck is showing. Even if only the neck is showing. If it goes down and only this little is showing, at this stage also, no matter how much load you have inside, the upthrust is still equal to the weight. As far as it is floating, upthrust must be equal to weight. As far as it is floating, when I mean floating, it doesn't mean it's completely out of the water. No. At least it is not totally sunk, immersed. It's still, part of it is still outside, so it's floating. So, as far as it is still floating, upthrust at that point equals to the weight. When the load is inside, I have lots of load inside here, inside the ship, so it sinks a little. I am saying I still have the weight equals to the. Now I know when it sinks like that, the weight now increase so much. I said the weight was equal to upthrust, the weight increased because I put some load inside. When I have load inside, When I have load inside, it was like this before. When I put load inside, it starts going in, going in, going in. So the weight increased. Before it goes in, I said the weight increased. When the weight increased, why will it go in? That is what the question is asking us. Why will it sink when it is loaded? That's what the question is asking us. The question says, why it will be lower in the water when loaded? We know that the weight has increased now, and for it to float at any level, weight must be equal to the upthrust. What then happens to upthrust? Upthrust has to increase. Upthrust also has to increase. Upthrust must also increase. This Mr. Upthrust must also increase and be equal to the weight. What will make upthrust increase? What is upthrust? Weight of the displaced fluid. So the amount of water displaced, has to be higher. The mass, the weight of the water displaced has to be more. The volume of the water displaced has to be more. So that is why it displaces more water, because it needs a bigger upthrust this time around to balance the new weight. It needs a bigger upthrust to balance the new weight, because the weight and the upthrust must always be balanced. So now it needs a bigger upthrust. This is the weight, sorry, and that's the upthrust. This was the weight. Weight has increased, so upthrust has to increase. This is weight, not upthrust. This is upthrust. So weight increased first. So for it not to sink totally, upthrust has to balance it. You need more upthrust. What is upthrust? Weight of displaced fluid. So the fluid, more fluid has to be displaced. So it needs to sink in for the fluid to. Once the fluid rises up the side, then it sinks in. That is the reason. So I hope you understand what I'm saying. You have to write down what I'm saying. You have to write down the answer. You should understand, then go back and look at the questions again. When the upthrust, the weight is increased when it is loaded, then upthrust has to balance it if it must float. Therefore, how will upthrust balance it? Upthrust is the what? Weight of the displaced fluid. So more fluid needs to be displaced. Don't forget, upthrust equals to density of fluid, which remains the same, volume of fluid, and G. This remains the same, this remains the same. For this to be increased, volume of the fluid has to increase. So volume of the fluid increases. Explain why the marking of tropical fresh water is higher up the side of the ship than the marking of the tropical salt water. Same principle. What they are telling us here is that now we have this ship. They said, explain why tropical fresh water is higher up. That means the ship will go down because this mark is higher up. That means the ship will go down to get to that mark in tropical fresh water. But if it is in tropical salt water, it will not go so much down. That's what they are asking us. That means they are telling us that it will go, the line, the water level will go up here. That means it displaces more water in tropical fresh water than tropical salt water. That's why this level is down. The level at the side of the ship is down here. So what is responsible for this? Listen. First, you know that for it to float, upthrust must be equal to the weight. Upthrust must be equal to the weight for it to float. Now weight is constant. You have loaded your ship and you are moving. Loaded or unloaded. Your ship crossed from tropical salt water to tropical fresh water. What happens to it? Now, weight is constant now. But the density has changed. Look at the question. The density has changed. Density of salt water, the density of salt water, of tropical salt water, is higher than the density of fresh water. The density of the salt water is higher than the density of the fresh water. Fresh water has low density. If you listen to this, if you watch this video, you understand what I'm trying to say. My video on this topic. So that means if updraws must be equal to mg and mg is constant, that means mg equals to updraws in salt water, which is equal to density of salt water multiplied by volume of displaced salt water times G. If suddenly it goes into fresh water, again, weight remains the same. It should be equal to updraws. That means updraws should be constant. If updraws is going to be constant, the same as weight, because weight should not change, so updraws should not change, no matter which water it enters. If it let it enter the water of mercury, it doesn't really matter now. Now, density of fresh water, volume of displaced fresh water times G. Remember your math here. Answer has to be the same. The answer here should be the answer here. For me to get the same answer, if this is constant, this is constant. If this is now reduced, density is reduced, something has to increase to give me the same answer. It's like I'm saying, I have to get my answer to be 20, and I have 5 times 4 times 1 to be equal to 20. And I have to get 20, but fresh water has low, very low what? Low density. But 5 has changed. 5 has become 2.5. The density has changed. Maybe it becomes half. Times, this one must be 1 because it's constant. What happens here? Something must happen here for me to get 20. This has to be increased. It has to be 8. Just like that. Nothing goes for nothing. Something has to suffer for it if I must have a constant answer, because mass and weight must be the same, because I have not added to the weight, so the weight is not, weight and updraws must be the same. I have not added to the weight, so updraws will not change. If updraws will not change, but what makes up updraws, density times volume times G, one of them is changing, the other one remains constant, this has reduced. Of course, something has to change. Volume of displaced fluid, fresh water fluid, has to increase. So, we said, updraws must be equal to weight for it to float. So, if that is the case, you can write all this if you want to. Density of the displaced, since the fluid here has a higher density than this fluid here has a higher density than the fluid here. Salt water has a higher density than the fresh water. And from this formula, therefore, since G is constant, this has to increase. Volume of displaced fluid must increase. So because of that, it lowers down in the fresh water. It goes down in the fresh water. That's why the marking is up there. We already know that to move up there, it has been calculated. So that's why the mark is up there, because it will displace more fluid. I believe you got that. Okay. Question number 2B now. A student devised a simple experiment to demonstrate the change in the position. Same thing that was happening there. It's what is happening here. This is the sea, this is the sea water or the fresh water, whatever, and this is the ship. Same thing. And don't forget the hydrometer I showed you. One of the application I call that video, applications of Archimedes principle and updraws, or applications of updraws and flotation. I gave you lots of applications. This is one of them. Beam saw line. The hydrometer is one of them, and the some other things right there in the video you have watched. Now, this can act just like the ship, and this the water. A student devised a simple experiment to demonstrate the change in position of a ship when in water of different salt concentration. The student placed a straw sealed and weighted at the bottom into a test tube containing distilled water. The length of the straw below the surface of the water was measured. The student has a test tube here with some water. He now got a straw, the one you used to drink. Then he sealed it at one end and he put some heavy object like stone or sand there to make it heavy, to make it a little heavy. And he dropped it here. So because of the weight of the straw now, it will displace some water. Sir, you agree with that? It will displace some water. Now, let's assume it has displaced this amount of water. Let's assume that it has displaced this amount of water right here. So the student placed the straw sealed and weighted at the bottom into a test tube containing distilled water here. The length of the straw below the surface was then measured. So let's assume this is the distilled water, and the length below the surface was then measured. The straw settled in a position so that the length below the surface of the water was 13.3 centimeters. The experiment was then repeated using water containing 20% salt. 20% salt solution. Note, this 20% salt, for those of you who are chemistry students, you already understand. It does not, you are not going to use this 20% in your calculation. It's just telling you that a more concentrated solution, a salty solution. Instead of them to tell you salt solution, they just said 20% salt, containing 20% salt solution. Calculate the length of straw now below the surface of the water. Density of distilled water is this. Density of the salt water is this. Don't forget, the weight of the straw did not change. Whether it is in salt water or in distilled water, the weight remains the same. Don't forget that. And for it to float, upthrust and weight have to be the same. That means upthrust also did not change. The weight did not change, upthrust did not change. What then changed? Just like what we have done before, but in calculation form now. So let me say that mg equals to upthrust, and upthrust equals to density of fluid, volume of displaced distilled water times G. Volume of distilled water, density of distilled water times volume of displaced distilled water times G. I take the displaced water to be the volume here. Don't forget that. For the salt solution, the same thing. Mass did not change of the straw. It's also equals to upthrust. Upthrust here and upthrust here must be the same, because the weight is the same. The weight has not changed. Upthrust will only change if the weight changes for it to flow. But now upthrust, the weight did not change, so upthrust will not change. So upthrust, which is equals to density now of salt water times volume of displaced salt water times G. We are saying the upthrust here and the upthrust here are the same because the weight here equals to the weight here. If that is the case, can I then say upthrust here equals to upthrust there? Can I say this value equals to this value? Of course I can say that. So the question they're asking you is, calculate the length of straw now below the surface of the water. You see, it's a trick. You already know that since this salt water has more density and G is the same, just like the previous question, volume here will be different from the volume here. It is the volume we are interested in now. Volume will be different. Since the salt water has higher what? Higher density, the volume will be less. The volume will be less than the volume here. Just as we said before about the amount of water displaced, the weight of the water displaced, the upthrust is the weight of the water displaced. So, but something has increased, volume has to be less so that you get the same upthrust. Now, we are now saying, let's equate them together. But before we equate them together, V of displaced distilled water equals to volume equals to area times length. Now they have the same cross-sectional area because we are using the same what? The same test tube. So area times length distilled, length in distilled water. Volume here of salt water equals to area, because it's the same area, times length salt. So instead of me to, I'm going to equate this together, but instead of me to write this and this, I'm going to write this one in here and this one here. So what will I write now? I change my pen to some red. So I say now density distilled times, instead of volume distilled, I write area times length distilled. This is volume distilled, don't forget that, times G equals to, since upthrust is the same, density salt times, instead of volume of displaced salt, volume of displaced salt, I write A times L salt. Area is the same, cross-sectional area of this is the same, and of this is the same, times L salt times G. You can see they are equal. Instead of them to say find the volume now, the new volume, they're not talking about the volume displaced, they're talking about the length inside. So that's why I'm assuming that this length is the length of the water displaced, and the volume around it is the volume of the water displaced. So I'm not interested in the volume now, I'm interested in the length. So area will cancel out, you know that. So from this side, area is present here, area is present here, G is present here, G is present here. What do I have? Density of this times the length equals to density of this times the length. You know the density of the distilled water is in your question. You know the length of the distilled water is in your question. You know the density of the salt water is in your question. The only thing you are looking for is length of salt water. As easy as ABC. You can use your calculation and get this. Just place the things in here, and this is the only thing you don't know. Then it should be easy. Just put it in and find your answer. In your question, this is there. Please, before you solve this, I have the question there also for you, or the link to the question. If it's on YouTube, you have link to the question. If on my website, you get the question directly. So this question, you have to have it in your hand, the question I'm solving here, so that you can solve it and get your correct answer. The marking scheme is also going to be there so that I can cross-check. So that's it. That's how to solve this. So you get what you are looking for. It's 5 marks. 5 whooping marks. Easy mark to get. You just have to know that it is the volume that will change. If the density has changed, volume has to change so that the upthrust will be the same. For it to float, upthrust must be equal to the weight. And since it is still floating, upthrust is equal to the weight. If density changes, volume must change. G will not change. Another flotation, another liquid fluid flow. This is gas now. The designer of a new lorry trailer claims it will save 10% of the amount of fuel used compared to a traditional trailer. The photographs show the airflow. The photographs show the airflow around the traditional trailer and around the new trailer. From the photograph alone, when you look very well at these two photographs, it's just like you are playing with your father's your magazine, and you see, or when you were in primary school, spot the difference. You see differences already. This one is coming with sharp angles, and you can see, look at it. After the sharp angle, what do you see? You see turbulence. Sharp angle here, sits some turbulence. But look, smooth. When the here is sharp, this is smooth. Where this is sharp, this is smooth. So because of that, you see less turbulence here than there. So you see more turbulence there. Just from the diagram. You now know that the traditional trailer is not as streamlined as the new trailer. And if it is not as streamlined, that means it has more sharp angles. If it has more sharp angles, that means after the sharp angle, liquid flow past the sharp angle, there will be turbulence after. The sharper the angle, the more the turbulence. So, using information from the photographs, okay, you already studied the photographs. By seeing it, you already spot the differences. Explain why the new trailer will use less fuel compared to the traditional trailer. Yes, they told you to use less fuel. Why will you use less fuel? That means if this will use less fuel, that means it is doing less work. It doesn't have extra work. They are the same engine, the same weight, the same mass. Why will this one do less work than this? Why will this one consume less petrol, fuel, diesel, or whatever than this? Because it's doing less work. Because work done, because it's change of energy. If the amount of energy change, when this one travels the same distance as this, is less. That means the work done here is less. Why will the work done here be less? Something will come to your head. What is different in the diagram? There is turbulence here because it is less streamlined. Walk along that line. How many marks? 4 marks. First, you have to tell them that this new trailer is what? It's more streamlined than the old trailer. So the old trailer has more sharp angles and therefore more turbulence around it. The diagram clearly shows also that more turbulence around it. So, turbulence, where will you get the energy from? From the movement. From the movement here. And this will be formed. Remember when I told you in my video of liquid flow, if a liquid flows past a sharp angle, you have eddies formed, that's turbulence. And if it now continues later to flow in a streamlined manner, what happens to the speed before the turbulence and after the turbulence? After the turbulence, all things being equal, after the turbulence, it will be slower. Why? Because some of its energy has been used to form the eddies. For the turbulence, work has been done against the drag force. The one with the turbulence will have more drag force. Sure. Because it has more drag force, the trailer here, the traditional trailer, will do more work to overcome. We first do work to overcome the drag force before thinking of doing work to move. So, it's going to move the same distance as this, but first it has to fight the turbulence. It needs energy to do that. Don't say fight in your writing. So, it uses some of the energy to overcome the drag force associated with the turbulence. It uses energy to overcome the drag force associated with the turbulence. We first said it is what? This is more streamlined than this. This is less streamlined than this one. Because it is less streamlined, it has sharp angles and it has more turbulence flow around it, more eddies form around it. Energy is required to form this turbulence. or you just say work, or the trailer has to do work to overcome the drag force associated with the turbulence. Because the more the turbulence, the more the drag force. So energy has to be used. So for that. So if that is going to be done, it will consume more fuel than this. Even though they are going to move the same distance, they have the same engine, but it needs to do more work than this one. Because first it has to work against, it has to do some work to overcome the turbulence and the drag force associated with the turbulence here, which is not here. And then it will now spend more energy just like this. So this one is spending double energy. One energy as this, same energy as this for the motion if they are moving the same distance, same. Now, another energy here to overcome the drag force associated with the turbulence, which you have less here. So that's why you have this one consuming less fuel. You see, we talked about streamline, we talked about the marking scheme, may talk about sharp angles or not. Streamline has talked about, I've covered that. We talk about the fact that there's turbulence and there's drag force associated with the turbulence, and that work has to be done against the drag force in this one. So more energy, extra energy is needed for that, which is not needed here. So this one uses less fuel, consumes less fuel. Using information from the photograph, I've just answered that. This is another one. I think this will be my last question. The photograph shows a lava lamp. This is a lava lamp. You know it. You all know it. Some lamps you use to decorate, for decoration. That is a wax drop inside. When the lamp is switched on, large drops of the liquid wax are seen to rise and then fall within the clear liquid. There's a clear liquid, there's a wax drop. When it is switched on, large wax are seen to rise and then fall. As a wax drops, it is heated. It is heated. When heated, it expands, its density decreases, and it rises through the clear liquid. I know in your O level, GCSE or IGCSE, whichever one you are doing, or SSCE, you must have studied something like this, that when we hit it, it expands. When something expands, what happens? Then the volume increases. So density is equal to mass over volume. So density decreases below that of the liquid. The other part of the liquid, then it flows. You cannot write that here. I know many students will write that. You know why you cannot write that? They already told you. They told you it is heated. They told you it is expanded. It expands. They told you density decreases and it rises. So why should you write what they have told you again? They already told you that. So you don't need to write that. The reason why that thing that happened that you study in IGCSE or GCSE or O level or SSCE, the reason why it happened is what they want you to say here. Now, okay, they say explain why. Explain why the wax drop. Explain why the wax drop begins to move up as it is heated. Why it begins to move up as it is heated. Now, we are going to use hot thrust and flotation here again. When it is heated, the wax is heated, it expands. You have liquid around it, clear liquid around it. When it expands, it displaces what? More fluids. the volume of fluid displaced increases. If the volume of fluid displaced increases, don't forget that up thrust is equal to density of fluid, which did not change, volume of fluid times G. If the volume of the fluid displaced is increased, that means up thrust of the clear liquid on the wax increases. Because the wax expanded, so it displays more fluid. That means if it displaces more volume of fluid, that means up thrust has increased because of this equation. This is the same, but this increased. So this has to increase. Because the up thrust is increased now, when it was here, floating here, weight and the up thrust was the same. That's why it was floating at that level. At this level. That's why it was floating at this level. Weight and up thrust the same. Now up thrust has what? Up thrust has increased more than the weight because the drop now expanded. When it expanded, volume increased, therefore up thrust increased. So it displaced more fluid. So up thrust increased. So your answer would be, initially when it was floating, weight equals to up thrust. So it was at that level. It was floating at that level. When it expanded, the volume of the wax, which is representing the solid now, increases. So it displaces more liquid. Therefore, up thrust becomes higher. The fact that it's expanded did not mean that the weight has increased. Weight is the same because it contains the same mass. It contains the same number of matter, the same mole, the same amount according to you in chemistry, mole. So the weight did not change. But the volume has increased, so it has affected the amount of the weight of the water displaced, which is the up thrust, which is this. So up thrust is now higher than the weight. So what happens? It moves. The force going up is higher, so it moves up. So it moves up. Because this force pushing it up is more. The up thrust pushing it up is more than the weight now. So that's why it floats. Again, it expanded. There's an increase in volume, but the weight remains the same. First, tell them that when it was at rest, when it was floating at this level, up thrust equals to weight. So when it expanded, weight remains the same, but it has displaced more volume of liquid, so up thrust increased more than weight, so it moves up. So there is a resultant force now upward, so it accelerates upward. That's why it moves up. So you get your full mark there. You get your full mark there. We have 3 marks there. The wax drop accelerates initially. Of course, it accelerates because there's a resultant force. Now remember that, because there's up thrust minus weight. There's a difference now. There's a resultant force. Up thrust minus weight now. And then reaches a terminal velocity. Write a word equation for the forces acting on the wax drop when it's moving upward at its terminal velocity. When it's at terminal velocity, what happens? What happens? As it is rising up, as it is moving up, what happens? There's a third force. When it was at rest, one of those 2 forces, weight and up thrust. But as it is moving up, a third force is introduced. Don't forget the drag force. Because it's moving now, moving fluid. A third force is introduced called the drag force. So drag force is introduced. So that means now, as it is moving up, drag force, you have up thrust, which is very big. You have the weight, which is small. Drag force starts coming in. Drag force because it's moving up, drag force is opposite, always opposite the motion. Because it's moving up now, drag force is always opposite the motion. Don't forget that. So drag force starts increasing. Drag force starts increasing until drag force and this is not up thrust, this is drag force. This is up thrust, drag. Until the drag force plus the weight equals to the upthrust. The drag force was not there before. But immediately this starts moving, as it's moving faster and faster upward, it accelerates. So it's moving faster. So drag force starts increasing as it's speeding up. So weight is the same until both the weight and the drag force equals to U. So the equation will be, because it's moving upward, plus upthrust, minus, because weight is opposite direction of motion, weight minus D equals to 0. Resultant force is 0 at what? Terminal velocity. When at terminal velocity, resultant force is 0, so there is no, that means upthrust is equals to weight plus drag force. If you must write figures like this, please, as I've been writing since, you have to tell the examiner what your symbols represent. Please don't forget that. I've been writing symbols since. Please tell them what your symbols represent. Even don't assume they know. You have enough time. These represent upthrust, this represent weight, this represent drag force. This is the equation they're looking for. Or you say U equals to W plus D. So at terminal velocity, you all know this. The wasp drop is seen to slow down as it reaches the top of the lamp. Explain why it slows down. This observation. The wasp slows down as it reaches the top. What happens? Why will it slow down? A lot of things can happen. You have 3 marks here. A lot of things can happen. What are the things that can happen? 1, as it reaches up there, don't forget that place is cool. Temperature decreases, 1. So the volume decreases again. It shrinks. That's what you call contraction and expansion. With temperature, solid expand. Most solid expand. Liquid expand. Except the anomalous or abnormal expansion of water. So it expands. But now up there, the temperature has decreased. It's gone down away from the heat. So the volume decreases. If the volume decreases, so it displaces what? Less amount of what? The clear fluid. If it displaces less amount of the clear fluid, what happens? What happens? Upthrust decreases again. So the wasp drop is seen to slow down. So as that is happening, as upthrust is decreasing, it is slowing down. It was moving with terminal speed before, but at a point it started slowing down because upthrust is decreasing, 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 decreasing. So it slows down. Because temperature decreases, upthrust, which was the major force pushing it, making it to go up, decreases because the volume, the body shrinks, or the volume becomes smaller, so it displaces less fluid, upthrust is reduced. If upthrust is reduced, that means it has to slow down. Upthrust is reducing gradually, not just once, so it slows down. Temperature increases, it reduces in volume, upthrust, it displaces less fluid, so weight of the displaced fluid, which is upthrust, reduces, so it has to slow down. It has to slow down. You get that? The temperature causes the whole thing now. Another thing is that look at what happens to the drag force when it slows down. Maybe we are coming to that. Okay, no. As it is slowing down, as upthrust is decreasing, it's slowing down, drag force is also decreasing, so something happens at the end. It may reach another terminal velocity that may be given to you in an exam, but don't forget, like you remember when you had the falling body, maybe what you call the paratrooper, what you call the falling a body skydiver that you did in your IGCSE. It can come out now also. It can be given to you. Go back and study that. Skydiver thing can be given to you still. It came out in one of the questions, and the mark was very high. And this is my last question. I have to solve it. I know you people are getting tired, but please, if you are tired, just switch off, go and play, come back and watch again. I don't have short videos. This is a serious business. You are doing A level or you are doing SSCE. It's a serious business. Lava is molten rock, which sometimes erupts from beneath the Earth's surface. Of course, we know this from geography. As the lava cools, volcano forms. The shape of the volcano is determined by the flow rate of the lava, of course. The graph below shows two viscosities of two types of lava. First, study the graph before you even look at any question. Of course, you can see two different types of lava and two different graphs. Viscosity here and viscosity here compared at all temperature. At all temperature. At the same temperature, viscosity of the rhyolite you can see is higher than the viscosity of the basalt lava. At all temperature. If viscosity is higher, that means it flows little. Some of you keep asking me, Tisha, can you define viscosity? For your level, just call it the resistance to the flow of fluid. Resistance to the flow, how the ability of a fluid to resist flow. To resist flow. Or the resistance to flow. That's the easiest way at your level. Now we have studied that. And we also ask something, they may not ask you, they may ask you, that as temperature increases for both of them, viscosity what? Decreases. As temperature increases, viscosity decreases for both of them. But it's more visible here than here. The rate of decrease here in rhyolite is higher here. That can come out for you as a question. So all those things, you have to look at them first. Okay, what is difference here? Okay, this one, okay, this one, okay, this one has higher viscosity than this at all temperature. Okay, then, okay, the viscosity here and the viscosity here decreases with temperature. Okay, and the viscosity here also decreases with temperature, but the rate of decrease here is higher than the rate of decrease here. You already almost killed it. The thing now is why that will be in your brain. But let's look at the question. The diagram below shows the shape of two typical volcanoes. Shield volcano. It has come out from the earth crust. Coming out from the earth crust, both of them, the lava. Of course, outside is cooler than inside. So, as it becomes cool, it becomes more viscous. Don't forget that. That's from this diagram. You know more about that. Both types of lavas are same at the same temperature as they reach the Earth's surface. Of course, they cool down to the same temperature, the temperature of the surrounding, we call room temperature here. The shield volcano is formed from basalt lava. This is from basalt lava. Basalt lava. And this is from what? From the cone is formed from rhyolite. Lava. I wrote it there so that I will not mix them up. Use the information in the graph to explain the shape of each volcano. 4 marks. By looking at the graph and this diagram, you already got your 4 marks. You know that at all temperature, basalt lava is less viscous than rhyolite lava. And when they came out, both of them have the same temperature outside. You see, as they come out, they have the same temperature. You have seen that. They cool down. When they cool down, they become more viscous and they solidify. Because is at a lower temperature. As they are ejected, they attain a lower, constant lower temperature, which causes them to become less viscous and solidify. But before they solidify, because this shield volcano is made up of basalt lava, it has flow, it is coming down more, it flows down faster. It flows down, for the same time it goes, it spreads out more distance than this. This guy, as it solidifies, it cannot flow too much because it's more viscous at that outside temperature. They are the same temperature, but they solidify. But just before they solidify, because this lava has higher what? The lowest viscosity, the flow rate is higher, so it has flown what? If it flows a longer distance, is spread out and flows a longer distance than this, because this is more viscous. This is more viscous. Before they solidify, they are the same temperature. This one already flows faster, the flow rate is faster, and is spread out a longer distance. That is the reason why shield volcano has the shape spread out, and this one is still a cone. Again, I've told them they attain the same. They've told you they attain the same temperature. You see, they cool down when you get to the outside to the same temperature, so it makes them more what? More viscous and solidify. But before they solidify, this already spread out because the flow rate is higher. It's spread out wider to a larger distance than this. You kill the question, and that's all. Student, that is the end of this question. It's been a long one. I'll have a part 2 to this video to solve more questions on fluid. Till we meet, it's been Teacher Hafiz, and I'm wishing you good luck in your tests and your exams. Good day and God bless.